Uh, in this very short video, we are going to derive an expression for the orbital speed of a satellite. So let us say this is the Earth, and there is a satellite which is revolving around the Earth. Right? Let us look at a few dimensions over here. The mass of the Earth we will call ME. The radius of the Earth will be indicated by, say, RE. And let us say the distance between the center of the Earth and the satellite is we'll call this R, right? And this R is this distance from the center of the Earth to this satellite, and this distance from the surface of the Earth to the satellite we'll call it H, right? So this is H, right? The height above the surface of the Earth at which the satellite is revolving. And let us say the speed of the satellite is call this as V0. So V0 is the orbital speed of the satellite, and it is moving around this particular orbit. Now, when this satellite is moving around the circular orbit, the centripetal force acts on this. The centripetal force is provided by this gravitational force of the Earth. So the gravitational force kind of pulls the satellite and ensures that it continues to move in the circular orbit. That means the gravitational force applied by the Earth is equal to the centripetal force acting on the satellite, because it is this particular force which is responsible for producing the centripetal force. And therefore I will equate the gravitational force and the centripetal force, right? The gravitational force will be G m upon r square, where m is the mass of the satellite. So this satellite has a mass m. So G m upon r square is the gravitational force. Let me write over here, this is the gravitational force, and this will be equal to the centripetal force acting on the satellite. Now the mass of the satellite is m and its velocity is v0, so centripetal force will be equal to m v0 square upon r. So I get this equation, G m upon r square is equal to m v0 square r, and this will, the m will get cancelled out, one r will get cancelled out, so I'll get G me upon r is equal to v0 square, right? And therefore I can write down v0 is equal to square root of Gme upon r. Now r, as we can see over here in this particular diagram, r is equal, this r, that is the distance from the center of the Earth to the satellite, is equal to radius of the Earth plus h. So I can write this v0 is equal to square root of Gme upon re plus h. Okay, let me call this equation 1. So I have obtained an equation for the orbital speed of a satellite, right, which is moving at a height h from the surface of the Earth and which has got mass m. But as you can see in this equation, the mass is not there. That means the orbital speed does not depend upon the mass. It only depends upon the height or surface, or the height from the surface of the Earth, right? There's one more equation that we will look at, and that is, we know that gravitational force mg is equal to G m upon re square. This is for any particular object of mass m. The gravitational force acting on it, or the weight of the object, is mg, and this is the gravitational force. From this I get G is equal to G me upon re square, and therefore Gme is equal to Gre square, right? And I will substitute this particular value, right? Let us call this equation to put above value of Gme in equation 1, right? So if I do that, I'll go over here now. I'll get v0 is equal to square root of, for Gme I'll write down Gre square, so I'll get Gre square upon re plus h, and this would mean v0 is equal to re upon square root of Gre plus h. Let us call this equation 3. Okay, so we have obtained one more equation for orbital speed. Of course, both of them are one and the same, right? Now, what do we conclude from this equation? What we conclude from this equation is that the conclusion 1 that we draw is that v0 does not depend upon mass of the satellite. So this is conclusion 1. Right? Conclusion 1 is V0 does not depend upon mass of the satellite. As you can very clearly see over here, mass is not there in the equation. It got cancelled out. Right? Mass got over here. We saw that mass got cancelled out, and therefore it does not depend upon mass. 2. What we can see is that V0 is inversely proportional to 1 upon square root of h. Right? V0 is inversely proportional. So the orbital speed depends upon the distance from the surface of the Earth to the satellite. So V0 is dependent upon h, and what this would mean is that as the height increases, orbital speed will keep on decreasing. So these are the two conclusions that we draw from this particular equation of orbital speed. Now let us take a situation wherein, let me go back to this diagram, wherein the satellite is revolving around the Earth very close to the Earth, right? So it is revolving, say for example, in this particular axis. That means it's very, very close to the Earth. In that case, h will nearly become equal to 0 because h is very, very small as compared to the radius of the Earth. If the object is revolving in this particular, h will be this, and that is extremely, extremely small as compared to the radius of the Earth. So we will say h is equivalent, or h is nearly equal to 0. So third case or situation I'll take is that if h is very, very small as compared to radius of the Earth, then I'll take h tends towards 0, and therefore V0 will become equal to, putting this h is equal to 0 in equation 3, I'll get Re upon G upon Re, and that will give me V0 is equal to square root of G Re, right? Let us call this equation 4. Right? Now these are constants, right? We know the value of G, right, and we know the value of the radius of Earth, so I can write down this is square root of 9.8 into radius of the Earth is 6.37 into 10 raised to 6 meters, of course, right? 10 raised to 6 meter, and if I find out this particular value, I will get equal to 7.9 into 10 raised to 3 meters per second, and this is nearly equal to 8 kilometer per second. So V0 is equal to 8 kilometers per second, right, when h is very, very small compared to Re. So what I conclude is that the speed of the satellite revolving very close to the Earth's surface is nearly 8 kilometers per second. Okay. With this, we complete our discussion on orbital speed of the satellite, and in the next video, which is a kind of continuation of this particular topic, I will look at the period of revolution of a satellite around the Earth. Thank you.